So far, we've been looking at what happens when we add heat to a system. So basically, we understand that by adding heat to a system, we can change the internal energy. And if we're changing the kinetic energy, then that heat that we add is going to change the temperature. So in cases where there's no phase change, we can use that equation to basically talk about how heat is going to affect the system. However, there's a different process that can happen other than changing the kinetic energy as we add heat to the system. This increase in internal energy can basically affect the bonds between molecules or between atoms. This leads to what we call a phase change. Now the equation is a little bit different. There's no longer a temperature change, okay? The heat that we add is going to change either a solid into a liquid into a solid. That's where we have the latent heat of fusion, or we can change a liquid into a gas or a gas into a liquid. That's where we have the latent heat of vaporization. There are even the possibilities of more exotic transitions that can take place, such as sublimation or condensing directly from a vapor into a solid. But basically, the heat that we add to a system is going to change the phase of this system, okay, where latent heat is in units of joules per kilogram. And once we multiply that by the mass in kilograms, we get joules back. Okay, let's take a look at this. Okay, so again, phase changes occur when the physical characteristics of the substance change from one form to another. First order phase transitions or phase changes can be melting or freezing, boiling, or condensation. And again, phase changes involve a change in the internal energy, the change in the potential energy, which is related to the bonds between atoms and molecules. But it's important to understand that there's no change in temperature as a phase change is taking place. Okay, this is a phase diagram, and this shows us typical phases that occur for a particular substance, and this is different for all substances. On this phase diagram, we have pressure in the vertical axis, we have temperature in the horizontal axis. And we can see that solids basically live right about here. We can do that. That was supposed to change into a pen. So our solid is here. And then we can have liquids over here. Pen's not really cooperating today. So there's your liquid. And then, of course, a vapor or gas is out here. Okay, so again, as we cross these different lines, we go from a liquid to a vapor, that's boiling. So we're going from a vapor to a liquid, that's condensing. Going from a liquid to a solid, we're freezing. Going from a solid to a liquid, okay, melting. All right, and again, there are some less common types of transitions that take place. We can sublime, which means we go directly from a solid to a vapor or a gas. Carbon dioxide does this. Actually, ice will do this. You know, if you ever put ice in a freezer, you notice it disappears. It does sublime, even without going above the freezing point. And again, frost occurs as we have water vapor go directly into ice. So there's going to be a latent heat associated with all these types of phase transitions. And whenever we are going from a lower energy phase to an upper energy phase, that Q is going to be positive. It's going to take energy to pull the bonds apart. If we're going from a higher phase to a lower phase, obviously that Q is going to be negative, which means we need to bring energy out of the system. So again, as we're going from a solid to a liquid, we need a positive Q. As we're going from a liquid to a gas, there's going to be a positive Q. And then, of course, the reverse involves removing energy. Okay? Now, the equation for latent heat as it relates to heat is Q equals plus or minus. Again, that gives us the possibility from going from a lower energy to higher energy substance or higher energy to lower energy of substance. M times L, okay? There's also molar heat capacity. Don't confuse that with some of the things that we have here. But here we're looking at how much energy per kilogram, okay, for the phase transition to take place. Now, this is very important because you can observe this on your own. We watch the temperature of a boiling pot of water as a function of time. And what we notice is if the heat is coming in at a steady rate, okay, we have heat coming in at a steady rate from a burner or heating element, whatever, let's say our Q is constant. We're adding heat to the system. What we notice is that the temperature will go up, okay? Fairly linear path, all right? Might be a little bit of a deviation from that because as it gets hotter, it actually does evaporate some water. But as soon as we hit the boiling point, okay, all of a sudden the temperature stops going up. We're at 100 degrees. Okay, we're at 100 degrees. So it can't get any warmer than that. And this will continue until all the liquid has been boiled away. Okay? Now, this gives water a really clear advantage as a coolant. One of the problems with water is it can be somewhat corrosive. But not only does it have an extremely large heat capacity, okay, it also has a very large latent heat of vaporization. Okay, why is this important for a car? Well, first of all, your car keeps itself cool. The engine, being an internal combustion engine, will circulate this radiator fluid to a radiator, which will then effectively disperse the heat into the atmosphere. But basically, the water, having a very, very high specific heat, is able to carry a tremendous amount of energy to the radiator where it can be dispersed. Even if that doesn't get rid of enough energy, let's say we go beyond what the heat capacity can take away, all right? The water can begin to boil, can begin to turn the liquid into a gas. You've probably seen pictures of a car overheating, and you've probably experienced it yourself. That water boiling is actually protecting the engine. It is turning the liquid into a gas at the cost of a tremendous amount of energy. As long as you don't keep driving the car, the engine won't damage itself as long as there's liquid coolant in there. So again, under normal circumstances, the water having a high specific heat is going to be able to transfer a lot of that energy from the internal combustion engine to the radiator. But if it exceeds the rate at which it can get rid of the energy, then we get into, well, it can boil off some of the water vapor, or can boil off some of the liquid water to become water vapor to get it additional heat away from the system. Now, hurricanes or other tropical storms are really good examples of how latent heat can power a storm. Many different storms are simply powered by the difference between hot and cold. You know, cold front moves through, and the transfer of heat in different air masses can lead to, fairly good winds. But it's really when we use the latent heat of water vapor that can tremendously increase the transfer of energy. All right, latent heat. First of all, where is it coming from? Well, on the surface of the ocean, as water evaporates, it's driving energy into the upper atmosphere, okay? Especially the warmer the ocean, the more evaporation that's going to take place. So what that does is that deposits more and more energy into the top of the clouds, okay? All right. Here's the thing. Once the energy is up there, we have this warm water vapor, which is expanded adiabatically. We'll talk about adiabatic expansion later on. And now it's become much cooler. It's going to fall down as rain. It doesn't sound like a big deal. But now this water, which has a tremendous amount of gravitational energy, is making its way back to Earth and turning that gravitational potential energy into kinetic energy. This kinetic energy increases the wind speed. As the wind goes downward, it spreads out. Coriolis force gets it going around in a circle. And before you know it, you have this extremely powerful storm, which is rotating in a counterclockwise direction in the northern hemisphere. Okay? So hurricanes are powered by the latent heat of vaporization of water. Okay? How do we know this? Well, because we don't get a hurricane unless we have warm water where the water can actually evaporate into a gas, into a vapor. So basically, unless we have a source of energy here, and this again is warm water, this storm is going to die out very quickly, okay? If the storm goes up to the north where the ocean water is much cooler, no latent heat to power this, or very little latent heat to power this. If it goes on shore where there is much less water or not much water at all, again, the storm dies out, okay? Essentially, the hurricane will gain strength as long as the latent heat available from the water exceeds the resistive forces which are trying to dissipate the energy from the storm. Now, we ourselves vaporize quite a bit of water just by breathing. You can actually see this here. And it doesn't just have to be cold out. Being cold out, it actually illustrates this. What's happening is, as a person breathes, the air is condensing into visible fog. Fog, of course, is an aerosol. It is water vapor droplets which are suspended in the air. And we normally don't see this water vapor unless it condenses. So right now, if it's too warm, you breathe out, you can't see that water vapor. But when it's extremely cold, you can see your breath in the form of this condensation. And this produces the fog that we see here. So what we know is we're always breathing out. We're always evaporating this water, depositing into the atmosphere, and this actually cools our bodies off. Okay, if it's really cold out, you can actually, keep quite warm by, breathing into a mask or using something that's not going to allow you to lose too much of the water vapor into the atmosphere. Now, we also sweat, and we'll get into that in a little bit, but if you're a dog, you don't have sweat glands. So the way that the dog is able to cool off is pretty much just by breathing, okay? You ever see a dog panting? Well, they're doing this for a very good reason. They're evaporating the water. They're turning it from a liquid into a vapor. And in doing so, we know that Q equals ml. The more water that they evaporate, the more they can cool their body. And again, we have an advantage over dogs because we can actually sweat. By putting water vapor onto our bodies, we are allowing this water vapor to evaporate. And with this, we can take heat away from our body, where Q is equal to mL. In this case, it's the latent heat of vaporization. Okay? If you ever watch on a really hot day, football teams will actually blow these misting fans. Well, what they're trying to do is simulate some of what we do naturally with our bodies. Instead of putting, water on the surface of our skin where it can vaporize, they're actually blowing water onto the surface, but also with the increased air by Bernoulli's principle, as we increase the speed of a fluid, the pressure drops. The drop in pressure increases the evaporation. That's another thing with the hurricane. The faster the hurricane gets going, the more it can evaporate water from the surface of the ocean and power itself even more. So here is how we cool ourselves off. In fact, we are always taking water from the interior of our body and sending it to the surface of our skin. Now, normally, if we don't need to cool off, we will go into what's known as a low flow mode, where the dermis will reabsorb the water and the electrolytes, okay? But when it's hot out, the dermis permits the water to make it all the way to the surface, and that causes us to sweat. And again, that's how we release the water into the environment. Now, unless it's humid out, you won't even notice that you're sweating. Unless it's humid out, this water evaporates so quickly that it's not even noticed. What the humidity does is it blocks the water from evaporating. If you've got a lot of water on your skin, right? And there's also a lot of water in the air, the rate at which the water is going to evaporate is going to be greatly diminished. And that really hurts our ability to cool. So when we look at something called heat index, the heat index is really related to how difficult it is for our body to cool. Heat index is a function of temperature. Obviously, the warmer it is outside, the harder it is for heat to go from the inside of our body to the outside, but it also includes humidity. Okay? The more water vapor that's already in the air, the more saturated it is, the more difficult it is to vaporize more water and cool our bodies off. Because really, again, Q equals ml. The mass of water that we can vaporize, not the mass of water that we can get on the surface of our skin, but the actual water that vaporizes or evaporates, that is going to be related to how much heat we can get rid of. So again, latent heat measured in joules per kilogram. If we're undergoing a transition from liquid to solid or solid to liquid, we call it the latent heat of fusion. Fusion means to put together. So if you're taking a liquid and you're fusing it into a solid, that's how we get the latent heat of fusion. Latent heat of vaporization, as its name implies, if we're evaporating a liquid into a gas or into a vapor, phase change is going to take energy away. It's going to take energy to go from that liquid to a gas. If we go the other way, we're condensing, then we're going to have to take energy out of this. Now take a look at this table right here and notice that water has very, very large amounts of latent heat, not only for the latent heat of fusion, okay, how much energy it takes to melt ice or to freeze water if you want to go the other way, but also how much energy it takes to evaporate water. So when we look at this right here, it takes 333,000 joules of energy to freeze 1 kilogram of water. And again, 1 kilogram of water is about 1 liter. So we need to take that much energy away. Or conversely, if we're going to melt the ice, we've got to add 333,000 joules of energy to that liter of ice. Actually, it's a little bit more than a liter, but that's okay. To boil off a liter of water, it's 2.26 million joules of energy. So really incredible amount of energy that it takes to go from a liquid to a vapor. And again, This is where hurricanes get their energy. This is where we are able to cool off. This latent heat of vaporization allows us to transfer a tremendous amount of energy just through this phase change, just by vaporizing water. Now, again, when we're talking about the latent heat of fusion, LF, we're talking about going from a solid to a liquid or a liquid to a solid. When we're talking about the latent heat of vaporization, liquid to a gas or gas to a liquid or vapor, whatever you want to do there. Okay? However, if we're below what's called the triple point is a point where a material can be in solid, liquid, and gaseous form at a certain temperature, at a certain pressure. If you're below that critical point, you will go immediately from a solid to a gas or a gas to a solid. This is true for CO2. At normal atmospheric pressure, dry ice or frozen carbon dioxide does not become a liquid, okay? It will simply go directly to become a gas. And you can see this for carbon dioxide, okay? This is the phase diagram for carbon dioxide. Here are the atmospheres. Here's one atmosphere. It is a solid at negative 78.5 degrees Celsius. So when we ship anything in dry ice, like for instance, they're shipping the COVID vaccine by Pfizer in dry ice, it turns directly into a gas, okay? You would actually have to go to a much higher pressure, 5 atmospheres of pressure, you will actually get carbon dioxide to become a liquid, all right? You know, sometimes you'll see trucks shipping around liquid carbon dioxide. I forget what they call it, liquid carbonic or something like that. That is pressurized carbon dioxide, which is cooled to a very low temperature. Now, let's take a look at, again, you know, taking 1 gram of ice. We're going to heat it from its initial temperature of 30 degrees below zero, negative 30 degrees centigrade, all the way up to 120 degrees centigrade where it's heated steam, okay? What does that entail? All right, well, if you're going to do something like this, you've got to alternate your different equations. Okay, before anything can be melted, we have to heat it up to its melting point. So if I want to take ice at negative 30 degrees centigrade, Celsius, and I want to heat it up to its melting point at 0, I have to use the specific heat of ice, and the change in temperature from negative 30 to 0 is plus 30, okay? It will take me, here's 1 gram, here's the specific heat of ice. Notice it's much less than that of liquid water, okay? It's remarkable that it's less than half the amount. And then again, we're going to go plus 30. Plus 30 degrees, okay? So 10 to the minus 3, 2 times 10 to the 3 times 30 gives me 62.7 joules. So first of all, here's the temperature. Temperature is going up from negative 30 to 0. Now the melting can begin. Okay, I'm at this point right here. Now, once I'm there, I have liquid water. Now I've got to switch my equations because I'm going from a phase change. I'm going from all ice to all water. Okay, during this process, I will go from 100% ice to 100% water, liquid water. Okay, so something's actually happening here. I'm turning more and more of the solid into a liquid until I get to this point right here. Okay, and again, I'm going to use another equation. I'm going to use Q equals, it's going to be positive because I'm going from the solid phase to the liquid phase, ml is going to be latent heat of fusion. So there's my equation right there. 1 gram, 333,000 joules per kilogram. It's going to take me 333 joules to heat that up. Quite a bit more than it took me, I'm sorry, to melt it. Quite a bit more than it took to actually heat that up. So I heated it up, I melted it, now it's all liquid water. I'm going to start the heating process again. Okay, so now I'm here. At 0 degrees, at 100 degrees. Okay, 0 degrees, oops, that's not what I wanted to do. So 0 degrees, I'm going to go up to 100 degrees. Okay, so again, whole new equation here. Now I'm going to do Q, but this time I'm going to do the specific heat for liquid water. Folks, be very careful here. Again, you saw that ice was 2010. Liquid water is 4186. Don't ever use a specific heat of liquid water when you're heating ice or when you're heating steam. And again, we can see there's how much energy it takes to go from 0 to 100. Okay, so now I have liquid water at its boiling point. And this is what's really, really impressive. Okay, I'm going to go from 100% liquid water, so here I'm water, to steam at 100 degrees. Okay? Again, here's my equation. Q equals mLV, 1 gram, 2.26 million joules per kilogram. So it's going to take me 2260 joules. Okay? To go from this point to this point. And now, finally, to heat the steam up to 120 degrees, I'm back to Q equals MC delta T, 40.2 joules. Again, remembering that the specific heat of steam is different from liquid water. Okay? Gotta be careful there. I want to make sure that all my things are correct there. Well, I don't have it on this table, but I may have made an error in terms of, no, I have the correct numbers there. Good. Now, when we have a phase change in a calorimetry problem, or a calorimetry problem, we have a calorimeter, we put hot and cold materials in there, they exchange heat, but the total heat of the system is 0 because we isolate it from the outside. Make a column for each quantity, just like you did for the calorimetry problem when we had specific heat. But allow for a row for each phase or phase change, okay? And also include another column that includes latent heat. All right, so what is this going to look like? All right. Here's a nice problem that illustrates this without getting into too many complications. All right, at a party, we have 6 kilograms of ice at -5 degrees Celsius. Okay, so here's my ice. I'm always going to call this ice. When it melts, I'll call it ice water. And that's to differentiate it from the other water, which is 30 liters of water, 30 liters of liquid water, okay? Oh, 30 liters of liquid water at 20 degrees Celsius. And again, oftentimes you can use kilograms interchangeably with liters because it's roughly a pretty good approximation. What is the temperature of the water when it comes to equilibrium with the ice. So let's do a little diagram right here. We're going to have liquid water. Okay. That's already here. And I know ice isn't, shouldn't be yellow. And we're going to have ice in here. That's going to melt and that's going to heat up. So the ice is going to give off energy. No, I'm sorry, the ice is going to, correct that. The ice is going to absorb energy, right? I'll use red for that. The ice is going to absorb heat, okay? And the water is going to give off the heat, okay? So the water is going to cool down, the ice is going to heat up. Now the problem that I have here is ice needs to go from -5 degrees Celsius to its melting point at 0, and then when it's ice water, it's going to heat up. So how am I going to do this? Well, let's set up our table just like we did in the previous section. Okay, I have the ice heating up, I have the ice melting, and then once the ice is melted, it's going to heat up to the equilibrium temperature. Okay, notice how I've set up this table, just like before. I still have Q equals MC delta T, okay? But alternatively, I also have Q equals M L for latent heat of fusion, okay? All right. So the water from the ice will always be 6 kilograms, okay? 6 kilograms of ice. The water that was already in there is 30 kilograms. Okay. So what do I know so far? I know that the initial temperature of the ice is going to be 5 degrees below 0. It's going to heat up to 0 degrees before it can melt. As it's melting, it'll stay at 0, but that's not even important for what we're doing. Once it's melted, it'll heat up and finally reach the final temperature. The water, on the other hand, will start at 0 degrees Celsius, and it will come to a final temperature after it cools down. Okay, what else can we do here? Well, notice that I put in the specific heat for ice, okay? I put in the specific heat of water because once the ice water is melted, it is liquid, so you got to use that C. Here is specific heat for liquid water, and here's the latent heat for latent heat of fusion for water. Okay, what can I do first? Well, the first thing I can do is just fill in the temperature changes. Again, we're going from -5 to 0. That's an increase to 5. There's no change here. We increase from 0 to TF. So TF minus 0 is just TF. And we're going from 20 to TF. So that's just TF minus 20. So I filled out this column right here. Everything is here. I don't need any more information there. Okay. Now, once I have that done, I can start filling out the column with the heat. Okay. Think about this. Once again, Q equals MC delta T. Q equals M LF. So I can fill that one out too. These two Q's are unknown because I have the mass of the specific heat. What I don't know is the final temperature. All right, so I'll do the first two first. I'll do the first two heats first. So I'll fill up here. Okay. So I do those calculations. The ice will take 6.27 times 10 to the 4 joules to heat up. That comes from this right here, okay? 6 kilograms. There's a specific heat of ice. It's going to increase by 5 degrees before it starts melting. So that goes up there. And then likewise, once it's melted, all right, I'm sorry, once it's melting, 6 kilograms of ice melting at 333,000 joules per kilogram. That is that value right there. Okay? So I have at least 2 of my Q's. Now, remember, this plus this plus this plus this is going to equal 0. All right? So let's set up an equation that sets all these different Q's, this one, this one, this one, this one, equal to 0, and then we're going to solve for TF in those equations. All right. Here is our first one. Okay. Let me use a different color. Here's our first box right here. That is going to go right here. Okay. But notice it's in terms of TF. The energy that the ice, after it melts, absorbed is equal to its mass times the specific heat of water times the change in temperature, which is TF. Okay? So this is going to go right in that box there. This one is the liquid water that was already there, which is giving off its heat to the ice. Okay? 30 kilograms, because there's 30 liters, 4186. Final minus whatever the initial was, that's going to give me a negative, and that's going to go in right here. Okay, so here are the 4 different equations. This one is this one is here, this one is here, this one is here, and as I said, they're going to add up to be equal to 0. We already did this one, we already did this one. We showed where this equation came from. We showed where this equation came from. And here's our equation. Everything's set to be equal to 0. Now identify everything with TF. TF is the only thing I don't know here. Here's a term with TF, here's a term with TF. So I isolate my TF terms, move them off to one side, move the other terms to the other side, okay? Divide by this on both sides, and we get, it comes to thermal equilibrium at 3 degrees. Okay, so that's a real nice latent heat type of problem. Sometimes you run into an issue where you don't know if all the ice melts. In the previous case, all the ice was gone. Okay, it came to a final temperature of 3 degrees Celsius. What about the case where only some of the ice melts? How do we treat that problem? Well, there we've got to be a little more careful, use a little bit of finesse. We've got 5 kilograms of ice, should be at 0 degrees, okay, in a calorimeter, which has 10 kilograms of water at 15 degrees Celsius. Now, sorry, it didn't show the 0. It should show the 0 there, but in any case, this is going to be a race. Is the ice going to melt completely before the liquid water reaches 0 degrees Celsius? Who's going to win? Okay, is the ice going to melt completely? Or is the water going to hit 0 degrees before that can happen? Now, I'm going to set up my table just like I did before. And I'm going to assume that the ice melts completely. And I'm going to assume that the water makes it to 0 degrees. Okay? That would be a real coincidence if that happens. But what this will tell me is Will it take more energy to melt all the ice, or will it take more energy to cool the water to 0 degrees? Okay, whichever takes less, that is the process that is going to happen. Okay, so I do my calculations. Well, to cool the water off, to reach 0 degrees, it would take 6.29 times 10 to the 5th joules. Okay, so it would take me 629,000 joules of energy removed from the water to make the liquid water that was already in the container reach 0. To melt all the ice, however, it takes more energy. Take 1.67 million joules to melt all the ice. So what does this tell me? Okay, the water can't give up enough energy to melt all the ice. So this process, okay, all the ice melting is not going to happen. Okay, the water is going to cool to 0 degrees Celsius, and the process is going to stop because they're going to be at thermal equilibrium. So I'm going to get rid of the ice melting and replace it with just the liquid water gives up 6.29 times 10 to the 5th joules of energy to reach 0 degrees, to cool from 15 to 0. Okay, the ice is going to absorb that, but only some of the mass of the ice is going to be converted into water. So I want to calculate how much mass that is. All right, notice everything here is now known. Everything now is now known. I'm just trying to find this value right here. So we have Q equals mL. It's a latent heat of fusion. I'm just trying to find M. M is equal to Q. There's my Q divided by my L. There's my L. And that'll give me the mass of ice that is melted. Okay, 1.89 kilograms. So again, we set all the heats equal to 0. Here's how much energy the water would give up before it hit 0 degrees. It can't get any colder than that. So the ice will stop melting at that point. The ice has to absorb an equal and opposite amount. Okay, we solve for the amount of water, ice that does that, and only 1.89 kilograms of the ice actually melts. So that's how you handle partial melting problems.